Good afternoon and welcome to the Smart Grid Educational Series webinar. I am your moderator, Erfan Ibrahim. We would like to extend our sincere thanks to Sedacom here in Milpitas, California, and especially Gary Sorkin and Man, the CEO of Sedacom, for providing us this delicious lunch here and an opportunity for all of us to network. This subject today, the electromagnetic compatibility, is a topic that is quite esoteric in our industry. And the reason has been that for the last 30 years, people have been studying electromagnetic theory in college like it was medicine, as opposed to thinking of it as the essence of modern civilization. And you see that especially in the digital culture that has developed over the last 30, 40 years, that there's almost an antipathy towards things analog, that somehow it's considered primitive, somehow it's considered yesterday's stuff, and it's all about digital. But what a lot of people fail to realize is that digital technology is nothing more than an approximation of analog behavior. And if you put enough bits into it, it almost looks like a continuum, so that the digital approximation to analog starts looking like analog if you put enough bits to represent the phenomena. But there is nothing fundamentally digital. It's all analog. It's just being represented in a digital fashion. So we should not forget physical phenomena that occurs in an analog way. And electromagnetic interference is that alarm bell that rings when you've developed all the digital technology, put in all the cybersecurity controls, and you think you've got a really great secure system. And then nature has a way of telling you otherwise. And I'm really glad that we're having this webinar now at a time that is especially busy on the surface of the sun. If you watch the sun, there's a solar flare there that is the size of Jupiter. And occasionally, it has had very rich food, so it has this habit of burping. And these huge globules of plasma come off the surface of the sun, and they cause huge interference problems for satellites, especially the satellites that are orbiting around the Earth, and require good communication back on Earth. So this plasma starts interfering. So this is a very timely topic because as we're moving to increasingly digitally based power systems. In other words, we're not just relying on Kirchhoff's law and Ohm's law to move electricity. We're moving to this two-way energy flow. We require an actively controlled network, and that requires communication, quite often RF communication, to carry the signals to the places where decisions need to be made and control needs to occur. But if there's electromagnetic interference in the way, and Jerry will give us some tangible examples of how major those interferences can be, it can disrupt the communication and cause serious hiccups in our power system. Now, if you think about it, we spent all this time and energy talking about cybersecurity and cybersecurity controls, but this is a type of physical security because there is a phenomena, an electromagnetic phenomena that is affecting the electric infrastructure. And it gives no credence to zeros and ones in cybersecurity controls. It will create noise. Noise has a way of eating up the signal. So the signal to noise ratio throws off. And when that happens, it's very hard to encode digital information on analog waves. So you have to understand how serious this problem is. This is not something that we can just give to a cybersecurity company or a physical security company and say, go do it. This is many, many people working together. And Jerry is going to tell us those intelligent people that have worked together in IEEE, in the various working groups, to develop a set of standards that need to be in place to provide the appropriate protection against this type of phenomena. So with that background, I'd like to welcome Jerry, who's been very active in these IEEE working groups, to tell us a little bit about electromagnetic compatibility, what are the sources of the interference, and then tell us the progress that they've made in the working groups of IEEE. So I'm going to move this into a full screen mode now, and welcome Jerry Ramie of ARC Technical Resources. Jerry.
Thank you, Erfan. I want to comment on coronal mass ejections. This presentation won't cover those, but they are a serious problem in the northern latitudes. And this is originally from SGIP, Smart Grid Interoperability Panel work, when the IEEE's EMC Society wanted to become part of that effort. We had to sell the idea of doing EMC to the Smart Grid Interoperability Panel, so we came up with a tagline. Smart grid can't interoperate if it can't stay operating. And I want to dispel that Gen Y or Gen Z rumor that hardware just works and everything is digital. As Erfan was saying, hardware just doesn't work in hostile electromagnetic environments like utility substations or out on distribution poles. I'm Jerry Ramie with ARC Technical Resources Incorporated. This is Smart Grid EMC Standards Harmonization. I'd like to thank the American Radio Relay League for funding this work for the last 2 years, even though it wasn't of any great technical interest to them. There was one of the standards I'll cover today that they cared about. They didn't want a ham radio operator to key up his legally licensed radio and have some distribution products stop working as a result. Even though they would be legally in the right, so to speak, there wouldn't be any winners in such an ugly confrontation. So with that, I'm going to give you some examples of the need for this kind of work that goes back many years. In the mid-1960s, the new solid-state analog components in protective relays were failing in utility electric substations. Failures were traced to oscillating voltages created from normal switching operations, not high current faults. The oscillatory surge withstand capability, or SWAC test, simulates those events and was first codified in the mid-1970s as ANSI IEEE C37.90.1, then a trial use standard. Test simulates the oscillatory voltage transients up to a megahertz and 5 kV on the control wiring resulting from these switching operations. All the major relay manufacturers needed to retest their designs to make sure they exhibited immunity to these simulations without false operations, or frankly, utilities wouldn't buy their stuff. In the late 1970s, the Faultstripping transformer differential protective relay knocked out a 380 megawatt steam turbine generator offline. It was caused by an employee keying a portable radio transceiver less than 1 meter from a protective relay rack. The story I heard was he had the radio in his back pocket and he was leaned over and he just backed into the thing and keyed it against the cabinet. Well, that brought it off. C37.90.2 came as a result of that event. It simulated radiated RF fields for testing the immunity of protective relays to this kind of RF threat. It was published as a trial use standard in December of 1987 in response to this event. Also in the late 1970s, the Faultstripping of a barge-mounted peaking gas turbine generator occurred. It was traced to an auxiliary interlocking relay with very low battery drain in case the plant lost power. It would go over to DC power. The relay's pulling coil had a very high inductance, several henries, to produce a strong magnetic field with very little current. When the external circuit would attempt to de-energize the relay coil, this inductance and the stray capacitance of the control wiring created an LC circuit discharging voltages up to 4 kV DC peak on the control wiring, rise times of 5 nanoseconds or less, and repetition rates from 2.5 kilohertz or higher, as high as 1 megahertz. Simulation of this burst waveform was first published as an IEEE standard, C37.90.1, in the early 1980s as electrical fast transit immunity testing for protective relays, and was cited in IEEE 1613 in 2003 for utility communications equipment testing as well. In August of 1997, the operators at the Haddam Neck nuclear power plant ordered photographs to be taken of the inside of the control cabinets for training purposes. The flash photography of the control panel interiors led to the false activation of the halon gas fire suppression system. The ceiling collapsed when the fire suppression system fired in a deafening roar, forcing the evacuation of the control room, and a notice from the NRC. In Southern Illinois on September 25th of 2001, a solid-state relay controller opened a transmission line for no apparent reason. The security guard keying the 470 megahertz handheld radio was found to be the cause. Once again, an RF threat. Once again, the victim was protective relaying equipment. Indian Point, New York, March 23rd, 2008. Emergency shutdown of a reactor at the Indian Point nuclear power plant was caused by signals from a worker's digital camera. Journal News, June 11th, 2008. Federal regulators said radio frequencies from a consumer Kodak C340 digital zoom camera operated too close to a control panel interfered with a boiler pump controller that provides water to 4 steam turbines. Quote, the direct cause was radio frequency interference from the camera. All that had to happen was for the camera to be on, unquote. More stringent specifications of the control equipment was clearly called for in this incident, since normal operation of a nuclear plant was to be susceptible to upset by nearby consumer electronics. This indicates an insufficient compatibility margin between the emissions levels from the cameras or other devices at close range and the susceptibility thresholds of the controls and their wiring in the cabinets. If that difference is as high as 10 dB, then your system is probably pretty reliable. If that difference is down to a few dB, your system's on the edge of failure all the time. And that's what happened here.
How far was that camera from the site? Where was the camera?
In the guy's hands.
He was on site.
The photographer was an employee. They opened up the back of the panels, which you shouldn't do, and then they took the picture, and then the pump controller went offline and did not set off an alarm, and it starved the cores of cooling water. They went into an organized shutdown. There was no release. However, the plant failed. It was taken offline by a consumer camera. Scary, huh? With the advent of cell phones and tablets that operate above a gigahertz, they're clocked at frequency above these older IEEE standards up to 3.5 gigahertz now. New RF hazards have arisen. Then reports of false operation of protective relay when its access door was open for maintenance. There's that story about the access doors again. Open for maintenance while a nearby cell phone or tablet transmits autonomously. The user doesn't have to tell his tablet or cell phone to do something, it just does. This testing gap at higher frequency is now addressed in IEEE 1613.1, completed in 2013, for the EMC testing of utility communications and networking equipment, which I'm going to talk about today. Big picture, trends in hardware are the miniaturization of the devices, resulting in smaller gaps in the geometries inside the chips. Lower power consumption for longer battery life, which results in smaller voltage swings inside, quieter signals inside the chips. Higher clock speeds, well above 3 gigahertz for modern PCs or laptops or tablets, make them sensitive to shorter, smaller external events. Wider bandwidth I/O ports, bigger highways to get in, which are more susceptible, allowing interference to enter the products. And all this results in increasingly vulnerable digital products. That's the reason why we wanted to get involved. Smart Grid Interoperability Panel formed the EMI Issues Working Group in September of 2010 to address equipment immunity and installed reliability. Of all the things we try to do, there are no reliability meters. But if your product or system exhibits higher immunity to external electromagnetic threats, it is by definition more reliable. And that's what this is trying to ensure. 8 months were allocated to develop recommendations for the governing board. It took us 27 months. EMI Issues Working Group report was completed in November of 2012. IEC 61850-3, which was in the NIST Catalog of Standards, was the best practice guide we used for determining which EMC immunity tests to recommend for addition to IEEE 1613, as there was a new addition coming up, IEEE 1613.1, which was an extension of the existing IEEE 1613 from 2009. These two standards, 61850-3 and IEEE 1613, were already widely used in industry as shown in their advertising, so it wasn't felt that these were a burden to American manufacturers. Is IEC 61850-3 relevant for this work? Absolutely. Recent advertisements in Power Grid International magazine indicate it's a sales feature. The link from the SEL ad on the left touts that their communications products are hardened to meet stringent IEEE and IEC tests for harsh environments, unquote. Cisco ad on the right notes that their ruggedized routers and switches already comply with 61850-3 and IEEE 1613 standards. It notes that the, quote, next generation networks will be based on 61850 standards as investment protection. So we felt that since industry was already doing this, we would codify that. In effect, we were catching up with what was already the reality on the ground, which is that American utility communications equipment providers were already doing this. IEC 61850-3 only addressed products used inside the substation fence, and it required these immunity tests shown on the right. 61000-4-6 is conducted RF immunity up to 30 megahertz. We don't use radiated testing for those long, low frequencies like the hams do with those huge antennas. We do this as a conducted test because it's easier to do the test. And the signal levels are more consistently delivered. 61000-4-16, radiated fields to IEEE C37.90.2, which already existed here in the U.S., so it wasn't a gap. I should point out here that we require a higher level of testing for radiated RF immunity here under the IEEE 1613 and 1613 pair, 20 volts per meter rather than 10 volts per meter. And we include pulse modulation up to 6 gigahertz, which is not included in the IEC version. IEC 61004-8, power frequency magnetic fields, 61000-4-10, damped oscillatory mag fields, -4-16, conducted common mode disturbances from power switching electronics, 61004-4, electrical fast transit, which was already covered under 3790.1. A terribly obvious gap was surge, 61004-5. American standards didn't require utility products to resist lightning strikes. Indirect lightning strikes 5 miles away. Well, if the vendors hadn't been testing for this, their stuff would have already blown up. So the truth of the matter is we were just catching up to what the reality on the ground was. American manufacturers were testing for surge. They had to, or the products wouldn't survive. Yes, Gary? Yes, Gary?
Jerry, what kind of specifications are there in Europe that compare, and how has Europe taken a proactive stance?
Yeah.
Can you repeat the question?
How are there tests in Europe? Yes. Each of the ones in black here, there's a European version of. For instance, for radiated RF fields, it would be 61000-4-3. For ESD, that would be 61000-4-2. EFT would be 61000-4-4, for instance. Surge withstand would be 412, for instance. The reason that if we found that the American document under IEEE was already doing the test, even if it was more severe or a different level or something, we didn't second guess it. We just concluded it was not a gap. The 5 shown in red here are the gaps, meaning there was no IEEE equivalent for this. We wanted to close these gaps and make the American IEEE regime similar as we could to the IEC regime for 2 good reasons. The first was we want to make an integrated set of documents that a manufacturer on either side of the ocean in Europe could test to one set of standards and sell here. America could test to one set of standards and sell over there. We also wanted to give American utilities or anybody else using IEEE standards, which are used outside of America, an opportunity to choose from a larger collection of better tested, more reliable products at lower cost. So it was the right thing to do. It's what the NIST SGIP wanted us to do. And I went over and joined the working group in the IEEE's Power and Energy Society to write the document 1613.1, which was going to fill these 5 gaps. Yes, sir?
Yeah, the IEC standards listed here, how are they different from the EN? Because the nomenclature is exactly the same, 61,000-4-
Yes. A Euronorm is taken from an IEC basic standard. Let's say that first one, -4-6. A Euronorm in the UK, for instance, would be a British BSI EN 61004-6. It is exactly the same document, word for word. So a Euronorm is an IEC standard that's been adopted by a country. The European Commission doesn't order countries to meet these standards. They order themselves. And as members of the European community, they adopt what the IEC passes as the law of their land, versus the UK we talked about. The gaps in American utility EMC standards. These 5 gaps from the previous page, in red, are referenced in the 1613.1 2013 standard. IEC 61850-3 invoked test levels and tests for the substation products that were copied into our document and called out for use inside what we called Zone A, that's inside the substation fence. And it's shown in the middle column. If you're a standards guy like me, I want to point out that these are the highest levels of tests for immunity. The strongest, the loudest interfering signals were used for Zone A inside the substation fence. So for each of the 5 documents, Zone A is as loud as that test ever goes. Zone B is defined in the document 1613.1 as outside the substation fence, out in distribution. And it's 1 level lower in every case, right from 61,006.5, the generic standard for power equipment immunities in the European Union. So with that, I'm going to move into now what I call the boring content part of the presentation, where I'm going to actually go through these 5 tests, hopefully as quickly and painfully as possible. Painlessly as possible. Any questions about how we got here? Where are the 5 tests? Why are we doing this? Excellent. Surges first. 61,004.5 surge immunity testing. Unidirectional overvoltages or surges are caused by switching or by lightning transients. Switching transients are associated with major power system switching operations like cap bank switching, minor switching operations near instrumentation or load changes out in distribution can cause them, resonance circuits used with switching devices like thyristors, or short circuit or arcing faults in the earthing system of the installation. Lightning transients are associated with direct lightning stroke to an external circuit. Usually that ends up with carbon everywhere. Indirect lightning strike that induces voltage and currents onto conductors, much more common, and what the test really simulates. And earth currents from nearby direct strikes coupled into the earthing network. The surge waveform is defined as the combination wave. That is 1.2 by 50 microseconds open circuit voltage on the left and 8 by 20 microseconds short circuit current waveform on the right. When your surge protective device fires, your product is neither an open nor a short during the test. It may look open at first, then you have a protective device fire, and then it looks like a short. So the waveform that's actually delivered to your product never looks this way. But that's how the waveform of the generator is called out. The reason being we specify the complex RF impedance of the generator doing it this way. Standard gives guidance on selecting the coupling method to be used. This agrees with Euronorm 55024 for computer equipment as well. Mains power is tested line to ground and line to line up to and including the test level specified. Symmetrical or balanced, that's telephone or Ethernet lines, are typically tested via arrestor coupling. Shielded lines are stressed 20 meters of the cable grounding between products, for instance, not on the center pins. AC or DC mains testing is shown here. Upper diagram shows a combination wave generator connected to a power line coupling for line-to-line coupling. Associated decoupling shown at the left. The lower diagram shows the generator connected line to ground, sometimes called common mode, on power lines. 2 kV, 1 kV, line to line, 2 kV, line to ground, or twice that for inside the substation fence on AC power lines. 5 positive and 5 negative hits are delivered each at 0, 90, 180, and 270 degrees at 1-minute intervals. That's 40 hits per voltage level, and all lower levels must be satisfied first. Wait your 1 minute in between or the product's going to get hot and fail. There's symmetrical or balanced lines that may connect directly to outdoor cables, like many balanced lines do. Analog modems, for instance, plain old telephone service, RG11. Testing uses the combination wave at 1 or 2 kV to ground common mode, depending on its location. For Ethernet pairs, by the way, we use the survivability method. We're still stuck with the same equipment, but I can only test 2 pairs at once, so I test 2 pairs. Then I test the other 2 pairs in the Ethernet bundle. And then I see if anything's left of the Ethernet front ends. This is often done as survivability with the product turned on, but there's no auxiliary equipment actually talking to it. We deliver energy into an operating front end, and then we check later to see if it still works, called survivability style testing. Shielded lines are direct coupled as shown in this figure. I want to point out that we're surging the chassis of one product, and the surge energy flows on the outer ground of the cable and then returns to EUT number 2's chassis. This is a test of the cable's bonding. We don't surge directly to the pins, nothing would ever survive. Once again, 5 positive, 5 negative at each voltage level called out. During that, EUT, during the testing, EUT is assessed for its acceptance using the criteria I'll show you later. Coupling, decoupling level, Conducted RF immunity testing simulates interference from intended RF transmitters operating from 150 kilohertz to just under FM radio. AM is applied during the test. 4 coupling methods are allowed in the standard, but only one of them is legitimate anymore. Coupling decoupling networks are now available for all kinds of IOs, including Ethernet. So there's no reason to ever use methods 2, 3, or 4. In fact, if you take your product to a test lab that uses any of those methods, you should probably be looking for a different test lab. Before the test begins, a level setting procedure is run through to make sure the required drive level is available. That drive level is then played back with 80% AM modulation applied on top, and during the test, dwelling for 3 seconds at each frequency. And the performance of EUT is monitored for its acceptance. Coupling, decoupling level setting procedure is carried out with 100 ohm series resistors you can see on the left. To each side, we short out all the lines, so it's true common mode. We place a 100 ohm series resistance and a 50 ohm termination to ground. On the left side, that 50 ohm termination is actually the meter's 50 ohm sensor. On the right side, it's a resistive termination. Assuming a 10 volt EMF level, you're looking for 17.4 dBm on the 50 ohm power sensor, which is connected to the power meter shown on the left. In 1% steps, that's 1.01 times the old frequency equals the new frequency. You'll get to a list of 633 frequencies at 3 seconds dwell each. It's about 34 minutes to do the test. You should also stop and dwell and check for susceptibility to this interference at your clock frequencies on your IOs and your main master clocks, as well as their upper harmonics. That list of amplitudes and the associated drive from the signal generator is the drive table that's played back during the testing. In this case, 60 hertz magnetic field. The document can be used for 50 or 60 hertz. Here we would use it at 60. Magnetic field testing simulates power frequency mag fields from nearby conductors or transformers that can upset power control systems. There are two threats we're trying to recognize here: steady fields from normal operating currents and short duration, much higher fields from fault currents. For inside the substation fence, level 5 severity has been called. That's 100 amps per meter for 1 minute, 1,000 amps per meter for 3 seconds. Drop that by a factor of 10 for outside the substation fence, 10 amps per meter for a minute, and 100 amps per meter for 3 seconds. Field uniformity for 1 meter square induction coils is given in this diagram. For the immersion method, the maximum EUT dimensions are 0.6 by 0.6 by 0.5 meters high. That's a common piece of rack mount equipment. If you make a common piece of racking equipment, you can use the standard 1 meter square induction coil. These power frequency magnetic field testing are all run by the immersion method. It requires that you rotate the coil or the EUT to all 3 axes, and you rerun the test with a COM port monitoring the EUT's acceptance on each axis if it has a COM port. And this has been written for communications networking equipment, so it probably has a COM port. Later on next year, when this standard is extended to everything utilities buy, including stuff that doesn't have a COM port, you're going to actually have to look at the product and determine if it's operating normally or if it's doing what its critical functions are. And you need to verify that EUT still either trips and resets if it's a relay or has its critical functions remaining intact at the end of this test. Oscillatory magnetic field immunity testing to 61416-10. Damped oscillatory mag field test simulates the magnetic fields generated by the switching of high voltage bus bars or isolators. The test mainly applies to electronic equipment that's installed in high voltage substations. Level 5 testing is required inside the fence, level 4 outside the fence. That's 100 amps per meter for 2 seconds, each waveform in all 3 axes. 1/10 of that outside the fence, 10 amps per meter. The peak current from the oscillatory generator is set to a validation current that you can measure. Typically it's 1/10 of what you're trying to deliver. So that first peak is critical. And the parameters, mostly the period, or T as it's shown here, either 1 megahertz or 100 kilohertz, are the 2 critical waveform validations that are required to be included in the test report. Conducted common mode disturbance testing simulates electronic power equipment in electrical plants, which generates frequencies well above the mains. Standard addresses testing at DC, and then separately from 15 hertz to 150 kilohertz in common mode only. This is for external threats. That's the reason it's common mode only. This is the drive table of levels that you're supposed to deliver. Level 4 inside the substation fence, or level 3 for equipment mounted outside the substation fence. That would be 30 volts EMF. Many manufacturers don't bother to put this dip in, by the way. Manufacturers I've worked with run this straight across. Level 4 would be straight across at 30 volts per meter, or 30 volts EMF. But you're allowed to do this dip. So for margin testing, as I mentioned, the manufacturers usually have critical relay equipment. They don't bother with the dip. They just run it flat straight across. If they pass, they pass. That means they have some extra 10 or 15 dB of compatibility margin that indicates the product will be reliable in the field. We usually see an audio amplifier used for the first 3 segments up to about 15 kilohertz. And then an RF amplifier is brought in for testing from 15 kilohertz to as high as a megahertz, certainly to 150 kilohertz, using 10% step sizes and a 10-second dwell time, while the acceptance of the EUT is assessed to the criteria I will show you. The 50 ohm test generator consists of a signal source connected to a power amplifier to the wall of a shielded enclosure, because it's going to transmit off the wiring if we don't. Inside, a 6 dB attenuator and the cabling constitute the test generator. We begin by setting the signal source to 100 kilohertz and adjusting its level to achieve 30 volts open circuit. That's 15 volts terminated into 50 ohms. That's 4.5 watts. That's 36.5 dBm on the sensor with a 40 dB protective attenuator so you don't cook the sensor. And that's the idea. Once again, we're going to generate a drive table at all the frequencies. Since this is resistive, it doesn't move around much. Same drive probably gives us the same power meter reading with slight variation. Test setup requires that the signal and contact I/O, CTPTs, shielded, balanced, and power ports of the EUT all be outfitted with couplers and decoupling devices before testing begins on any of them. An amplified 50 ohm source, like I showed you, supplies voltage to the coupling networks that are shown here. You ground the inputs to the coupling networks that are not being driven. So you have to get the EUT to survive being connected to the coupling networks. Now that it's working normally, we can open one of them and begin testing on the port. That's how this is done. For direct coupling, the EUT is connected to a 20-meter spool of shielded cable like RS-232, RS-485, or IRIG-B. The far side of the spool is connected to a decoupled auxiliary equipment. That's often optically decoupled, by the way, with a battery and a small opto isolator. The idea is you just float that in, and then the auxiliary equipment is not to be affected by the disturbances. It's been opto-isolated. And the reason there's a battery is because it doesn't leak into the power supply that way. So you can make sure there's no interference that gets to the AE. You want the AE to be removed from interference, but be able to see and talk to the EUT to determine if it's being interfered with. Direct connection from the attenuator's output is applied to the shield conductor only, shown on the red arrow there. And you make sure to ground this point as you would normally when it's not being driven. For coupling onto twisted pairs, the EUT uses a short connection to a T-coupling network whose values are given in the standard and shown here. Auxiliary side of the network is routed through a 20-meter spool of balanced cabling, like Cat3 modem or Cat5 Ethernet cable. T networks are affixed onto all pairs, and their inputs are tied together. Be sure to ground these common inputs when they're not being driven. My concern here about Ethernet would be that, as we've seen before, is that I'll have, this is one pair. I'll put 4 of these in series with the Ethernet line, and I can almost guarantee the Ethernet line will stop working. So what you may end up having to do is survivability testing. If you find that you put this network in series with your Ethernet cable, and it does not talk, and it used to talk. Therefore, you continue to deliver the energy as you were going to, but you'll have to check to see if the front end's okay afterwards. I'm afraid they don't give us a lot of choices about these values. So if it works for you and communication is happening, you use it. If it doesn't work for you and communication is not happening, you still have to use it, but you'll have to check it later to see if it's working or it was damaged. Some other features. The IEEE 1613.1 extension, which is 1613.1 2013, it includes several other features. For instance, there was no regulation of the COM cards inside smart meters. The dumb part of the meter, the revenue metering test, was covered under C12.1, but there was nothing about the COM function, so we took that on. Now the COM function to the card inside the smart meter has to be assessed using the 1613 and 13.1 acceptance criteria of the next line. Obviously, the meter has to survive these tests as well since it's a host for the card. So in effect, we've tested the meter too, but we're just trying to test the communications aspects of the card. Extended RF radiated immunity testing is required up to 6 gigahertz with pulse, up to 3.8 gigahertz with 80% AM, and up to 1 gigahertz with 10 volts per meter, 80% AM. So the IEEE pair has a tougher radiated immunity test, and it has a tougher ESD test. But otherwise, IEEE 1613 and 1613.1 equals IEC 61850-3 and IEC 61000-6-5, except for those two caveats. Also, differential fast transient coupling is now run on DC power terminals at or above 48 volts only. This is to simulate switched armature coils that back EMF arc across the floating station's battery terminals. This was a known source of disturbances originally addressed in 37.90.1 back in 2002. Very few people make this line balancing transformer T1. We actually wanted to get rid of this test, but we can't. It's an actual legitimate test, so if you need a line balancing transformer, you'll have to wind one. Good news, the instructions are included in the document. Bad news, it's not as easy as it looks. That acceptance criteria we've been dancing around about, it's here. 61850-3, our European model, borrowed, word for word, the IEEE 1613-2009 acceptance criteria, which is shown here. So did we. Since we are an extension, 1613.1 is an extension of 1613. Every word in 1613 applies in 1613.1. So we, at least on both sides of the ocean now, we are using exactly the same acceptance criteria. They borrowed ours and we agreed to allow them to use it. Our final drafting included this acceptance criteria from 1613-2009. It applies to Class 1 devices where recovered disruptions are allowed and to Class 2 devices where no disruptions are allowed, which implies an optical connection. This is something else that's different about the 1613 pair than the IEC pair of documents. We have Class 1 and Class 2, they don't. For them, disruptions are always allowed, no matter how severe. We have a special class, Class 2, for optical devices, where no disruptions are allowed. It's a pretty tough criteria to hit. We also included something from all those horror stories I told you up front. We called Clause 7.3 RFI hazards informative. This was the one paragraph we took out from normative. It says that your wiring should be consistent with the manufacturer's recommended procedure, and the UT should be tested with the covers closed. By the way, it should be operated with the covers closed too, as you've seen from the horror stories I told you earlier. Apparently, some owners of this equipment aren't aware of the hazards that can be exposed when the doors are open. I've shown you a few. Cell phones and tablets are transmitting autonomously. I showed you that. Misoperation caused by modern electronics within 10 feet of an open door. I showed you that. We would like you to place a warning label on the access doors telling your end-use customers to keep them closed, please. But this is informative. There is new work coming on a next revision. 1613.1 2013 is going to be opened up, and we're going to start again this year, in the next month or so. The IEEE Power and Energy Society had their first substation C2 committee in January, meeting in January in 2014 in New Orleans. Consensus of the committee was authorize a revision to 1613.1 that we had just finished, and not call it a new standard number like 1613.2 or .3, etc. The new scope will cover additional autonomous utility equipment that does not communicate. Stuff that communicates, stuff that doesn't communicate. Stuff that's inside the substation fence, stuff that's outside the substation fence. Pretty much anything a utility buys with a microcontroller or a microprocessor in it is going to be governed by the 1613 pair. It will apply the same tests and levels to practically all utility equipment in both substations and out in distribution. The idea was that not everything communicates, but there's a lot of new electronic devices coming out. So we have a new title for it. And I have a copy of the draft here. Instead of being a draft standard environmental and testing requirement for communications networking equipment installed in transmission and distribution, the new title will be for intelligent electronic devices installed in transmission and distribution, which is what the Power and Energy Society wanted the title to say. And they want a new scope as well, which was wider and broader. So we adopted the scope that we were told to use. I'll read it to you here in a second. The next version of 1613.1 The scope will be: standard establishes electromagnetic requirements for all devices or systems utilizing analog and or digital technology installed in transmission and distribution facilities. These devices and or systems may or may not include communications ports and may or may not be port powered. In effect, it's intelligent electronic devices, whether they comm or don't comm. I'd like to thank the IEEE Power and Energy Society Substation C2 Subcommittee Working Group that helped us on the 1613.1 extension, along with their chairman, John Tengen, for their enthusiasm in implementing the 5 gap immunity tests that were reported out by the SGIP EMI Issues Working Group and that I just went over with you. These efforts will finally lead to the harmonization of EMC testing for European and American utility equipment in both transmission and distribution environments. I'm Jerry Ramie of ARC Technical Resources Incorporated, and thank you for listening. Any questions about
Thank you, Jerry. And as the people online are going to formulate their questions, we'll take questions from the room. Just, Jerry, please repeat the question for the purpose of the recording and the audience online.
Yes, Gary.
Jerry, each of your tests have a threshold, which above which or below which, depending, will cause damage to the equipment.
They usually don't damage. These tests normally don't damage products except that lightning strike surge test.
Okay.
There you can actually cook your product.
Well, then the other ones for immunity,
yep.
What happens as a failure? The data from the interference gets assembled?
That acceptance criteria I showed you earlier, what constitutes a failure? We give you some interference stimulus that doesn't blow up your product.
Okay.
How do I know if I passed the test or not? That acceptance criteria I showed you, no disruptions, no resets, it still works at the end of the test. That's how you judge if you passed or not.
So those criteria levels were determined for natural phenomena such as Erfan sunspots
yes.
and plasma coming.
That's a special case of coronal mass ejections, but yes, they were to natural phenomena. But
deliberate attempts to interfere with these systems will pose more energy or more of a threat, like a terrorist attack using an EMC bomb.
They're not necessarily. The question was about intentional EMI and are these tests appropriate to guard against that kind of threat. It's a good first place to begin. There is an IEC working group on intentional EMI, and I believe there's an IEEE EMC Society working group on intentional EMI. That effort is now headed in this country by Dr. Bill Radasky of Southern California. So there is, the current consensus is that we're adequately protected by the tests I've shown you. I also didn't show you the other ones that were in black, the ones that we and the Europeans have already agreed that we're all going to be doing. That was another 4 or 5 tests. I didn't want to make this too long. But between the tests I've shown you, those 5, and the 4 I didn't show you, we have a pretty good feel that the equipment being installed out in the field won't fail of its own order. Is it foolproof, guaranteed to be immune from intentional EMI threats? No, but those threats are poorly defined as of yet. There is some commercially available equipment in Europe, particularly in Germany, that you can buy today that is designed to create intentional EMI. This is an electromagnetic weapon. I believe the manufacturer has been asked by the German government to pull the product and make it available only for defense agencies or NATO countries to buy. I believe that manufacturer has done so. But up until last year, anybody could buy it with a credit card.
I think the important point here is that there are a set of standards that Jerry has gone over that put you in the right zip code, if you may, for protection against electromagnetic interference. So it will handle 70 to 80% of what's out there. For the other 20 to 30%, you have to develop use cases. And against those use cases, you have to come up with very specific requirements and then provide the protection if the asset is valuable enough to justify the investment. Then, in addition, you also have to look at the subject of resiliency of systems in plural. So there may be an electromagnetic interference intentional attack on one system, but if you have redundancy set up, or if you have ways in which you can recover from such an attack, then it's not so important just to put all the protections on that system. You go into that emergency mode, and then you recover. In the same way in cybersecurity, we are doing that. We have a set of requirements that are there from the NIST 7628 document, or from the NERC SIP, or what the California Public Utility Commission has put in the cybersecurity guidelines. But that only gets you a certain way there. For the rest of it, you have to develop contingency plans. What happens if my system is compromised? And there's an escalation procedure that occurs. And in that, accountability is very important. So you have to make sure that you record what's happening, so that in the future, if there is prosecution, you can use that information against those who did it. But it's an ongoing, it's a cat and mouse, it's like Tom and Jerry's cartoon, basically.
Erfan's comments about resiliency are important. It may never be 100% positive assurance that a particular EMI attack won't cause damage, but there will never be a widespread EMI attack. I can't take a tractor trailer with a high energy weapon and put it here and then put it to the next substation up north and the next and the next and the next. If you want to do that much damage to a network, by golly, you should be using cyber tools. Electromagnetic attack is always going to be localized, and that thing I broke, for instance. It's also very hard to hide from. If we know that a particular substation was affected or a particular house was affected, we have a pretty good idea that the person was nearby. You aren't going to do this from across town. You're going to do this from right outside the substation fence, where you're often likely to get caught. So all this noise about intentional EMI, yeah, that's good that we resist that. But at the same time, it's highly likely that such an offender would be caught. We haven't caught the people that attacked the Metcalf station down in South San Jose, but they used automatic weapons. They didn't use electromagnetic weapons. They just fired at the thing and punched holes and oil leaked out. Pretty effective, kind of crude, but it worked.
The other thing that's very important is that by having the standard, you have a group of very intelligent people who have the experience in this field come up with a set of best practices. That's what standards are. They're best practices. So it started out with practice, then they improved on it, and then turned it into a best practice, and then they said, let's codify that into a standard. Why is that important? Because throughout the world, you may not have the same level of experience and intelligence available everywhere. But if you have the standard, at least you can develop a test plan and then execute it to get the results. That puts you in business, basically. So the 70 to 80% of the events that we're talking about could be addressed. That is a huge savings for asset owners.
This is the biggest news that's happened into the utility equipment business in 15 years since I've been dabbling in smart grid. The reason that we didn't suffer any negative reactions or tried to be stopped by equipment manufacturers is they're already doing this. They couldn't have sold products to utilities for the last decade if they didn't survive an indirect lightning strike. They were already doing this testing. They welcomed the fact that we were going to standardize it and make it the same as Europe, or darn near the same. Utilities loved this as well. They wanted to buy reliable equipment, but had no staff to develop these kinds of standards. So we did them a great favor. In fact, we can judge by their current reaction to the new draft, which they asked us to make, which we're just beginning work on. Instead of only 2 societies of the Power and Energy Society, that would be Substations and the T&D group, we also now have Power Systems Relaying Committee. All 3 of the major utility represented subcommittees on the Power and Energy Society want this new document. They want its scope expanded to everything they buy. It's not because it's a burden, it's because it's a blessing to them. It allows them to buy the consistent stuff that they could get in Europe. They get a bigger choice of better tested products, probably at lower cost. And manufacturers win too. They can go to a test lab once. My suggestion is that you run the IEEE 16, 13, and 13.1 pair, And then you can do the IEC tests you just passed, because they're all the same. The levels may be even slightly less, but their criteria is identical. So you can get all your testing done at the same time. And you have a consistent burden. You don't have to build one product for, you know, a hardened one for Europe and a less hardened one for America. Most manufacturers weren't doing that anyway. They were building world-designed products they could sell anywhere. So we were not opposed by utilities. We were not opposed by manufacturers. We were encouraged by both.
Let's take some of these questions online. The first one is from Michael Shea, who asks, would EFT cover the issue triggered by the impinging EMP, the electromagnetic pulse?
No, fast transient testing would not cover a high energy event like electromagnetic pulse. It's a 50 ohm source. By way of graphic demonstration, I could take a 50 ohm source and put my finger into the output and it wouldn't even shock me at 4 kilovolts because it's mostly an RF content and it would rub along my skin and go back down to ground that way. So there's no energy in the waveform. It only has the fast edge. Unlikely to ever cause damage, but highly likely to cause disruption, particularly into a product that it communicates or a product that is clocked, which is any microprocessor or digital device.
Okay. Next question from Ravi Sitapati says, most relay racks in EHV and high voltage or extra high voltage and high voltage substations do not have doors. They're just open racks. So what do we do now?
You buy products that are tested to the IEEE 16, 13, and 13.1 pair, because the cabinet, it has to live in its intended environment, and for you that's an open rack. Tell that manufacturer that you run in open racks and that he'll have to pass in an open rack. Remember, that comment about closing the doors was informative. It's not part of the document. It's just a story that we tell inside the document.
Then Michael asks, would the new set of standards replace the incumbent NEBS, the Network Equipment Building System?
No, NEBS, or the Network Equipment Building Specification, is for telecom equipment only. If you're selling central office equipment that's powered on minus 48 volts and goes into a telephone company's central office, that's NEBS tested. It doesn't have really anything to do with what utility equipment that goes into transmission or distribution facilities is tested to.
And if I recall, NEBS also has a set of requirements for physical durability.
Yes.
Which this is not covered.
Which we did not cover earthquake or flame. We didn't cover environmental at all. In fact, now even in the SGIP, it's still controversial to talk about EMI because it's considered an environment. An environmental resistance, you might say, like temperature or humidity or shock or vibration. But it's closer to cybersecurity in that it has fairly poor metrics, but it's system critical and you know it when you don't have it. So NEBS only applies to telephone equipment, and this is utility equipment.
Are there other questions in the room or online? We still have plenty of time. I know this is a tough subject and rather esoteric, because as I mentioned, a lot of people haven't been trained in this area in a long time. It was freshman physics, was the last time we were in engineering class, and then they just passed the exam somehow.
I just want to dispel that myth that hardware doesn't matter and that hardware always works. Hardware matters, and it almost never works in a hostile EM environment unless you have designed it for resistance to that and validated that design by robust immunity testing.
Yeah. The key thing here is, if you are not a domain expert in this space, is that you don't have to go back to college and learn this from scratch. What this is about is, if you are in an economic decision-making position, like you're deciding on authoring an RFP in which you are going to bring different vendor products in to support your power system. Now, this is not just limited to utilities, by the way. This is applicable to enterprise accounts where they are generating their own energy, in the form of distributed generation. It is very important for oil and gas type companies that have a whole power system that supports their oil and gas movement. And it's also very important for independent power producers whether it be large solar farms or wind farms or storage, all types of equipment that involves power, generation, transmission, distribution. So we're not just talking about the 26 investor-owned utilities and a handful of large munis who can afford this. No, by making it a standard, you can put this into the language of your RFPs and make sure that the next generation of products that you buy have this, because if you don't put it in the RFP, the vendors have no motivation to meet these requirements. There has to be a business case. Then the other thing is that integrators really need to know this, because as they put in the equipment and they test it, they got to make sure that it meets the requirements. So what the standard specification does is it simplifies a rather complex phenomenon from physics into a set of very simple rules. Your job as the economic buyer or as the integrator is to make sure that you meet these requirements, and trust people like John and like Jerry and others, you know, who are doing a good job here.
The big takeaway I'm hoping that you get from this lecture is that this is big news for utility equipment makers, sellers, as well as acquirers. If you own a server farm and you have a wind or a solar plant outside, you are a power provider. You now have Zone A and Zone B hardware on your property. The 1613 pair of documents applies to you well. The takeaway is have your products tested to 1613, 13.1 pair, and you can choose from American or European products that are similarly tested, that are all hardened, and a lower cost. Yes, acquirers, utilities let's say, should put this in their acquisition specs. And yes, manufacturers already are putting 1613, and by reference its extension 1613.1, they may not have known it, but they did. They have referenced this document. Your competitors are already doing this. My phone's been ringing for the last few months about large manufacturers wanting to meet this pair of documents and asking us questions about what our text meant. And we haven't given them any surprising answers. It means what you've been doing for Europe already, except you're doing it here now. So yeah, there's a few more tests that you were already running for your European products, but they're the same tests. So it's being well adopted, and the takeaway is that if you're an acquirer, specify it. If you're a manufacturer, say that you do it, and you will be building a reliable product that your customers won't be calling you up later and complaining about.
So in mathematics, if you study numerical methods, when you try to solve complex polynomials, you do it by what's called a predictor-corrector method. And that concept applies in real life too. Life is all about prediction, and technology is all about correction in that predictor-corrector mode. You're living life, you're taking pictures, and systems shut down, and then the technology has to come in to provide the protection for that lifestyle that you've created. So then the next time you use the camera in a nuclear power plant, it's not going to shut the boiler off and cause a lot of problems. So that's what I meant by predictor-corrector method. And you cannot just unilaterally develop technology divorced from life. Life creates the set of use cases on which you develop requirements and then build technology to meet those requirements, not the other way around. In the valley here, we are upside down here. We first build technology and then we try to figure out what are we going to do with it. It doesn't work that way. That's why there's no scalability in that. Look at all the successful companies. They go and look for lifestyles of people and then build. Apple is a very good example of that. They look at what people want and then they build the technology. In this business, you see all these standards that have developed. It's not because people didn't know physics or they didn't know electrical engineering. It's just they never thought that this combination of lifestyle practices are all going to converge in one place.
Apple's a good example. Apple used to have 3 or 4 guys that were working on EMC issues a decade and a half ago. Now they have a crew of 28, and all products are significantly tested, many of them to the same documents I've shown you, and other tests that they have either come up with or have adopted from the IEC or IEEE regimen. They over-test their product in ways that we haven't thought of to try to build a product that's reliable regardless of cost. And Apple's reliability is legendary for a reason. It's those 28 engineers over there on Valley Green Drive.
Just think for an example, during the 90s and early 2000s, if you told a network administrator that you're going to use a Windows-based machine to actually manage real networks, they would laugh at you. Today, they're not laughing as much. Those Windows-based machines are coming out into the field, especially in the power systems business, out in substations on ruggedized boxes. So if you don't have electromagnetic compatibility taken care of on those boxes, you're going to be out of business very quick. The data center is a nice protected environment, so there the Intel machines worked just fine. There was plenty of protection against EMI attacks, but not at a substation. And especially now with integrating renewable energy on the distribution system, those intelligent points are going further and further out of the substation. So there's even less protection against electromagnetic interference.
That's why we called out pretty severe levels out in Zone B, out in distribution. And we did no breaks to the smart meters, the COM cards inside the meters. They have to meet the same level of immunities that a cap bank controller or a tap changer for maintaining voltage has to meet. To us, it's just another communicating asset that's owned by a utility out in distribution, and it has to survive its environment.
Just think for a moment as electric bill. By the way, this is completely unrehearsed. We had no discussion before that we were going to talk this way.
We can do this one.
But it's happening spontaneously because as he's saying things, it's triggering things in my mind. Just think about the electric vehicle penetration that's occurring on our grid, and think of the impact that that has on the street line transformer. So that transformer cannot just be a piece of metal with some oil and a coil and some alternating current. It has to be an intelligent device now that knows when to cut off the charging of those vehicles if the cumulative load.
Let me see, we got an intelligent device that's connected directly to the mains and it pushes high current into low impedance loads.
Yeah.
What could possibly go wrong?
Yes.
Good news that what we've seen is that charging manufacturers, charging station manufacturers are buying this kind of equipment and doing this kind of testing. They recognize that there won't be any winners if you take your nice fancy electric car and you go up to the charger, you plug in and it dies. What did I do? Did I kill the charger?
Yeah.
Chargers have to be bulletproof reliable. That's what you expect.
Now,
you're not going to get it by accident.
Combine that EV charging with climate change and start thinking about all the thunderstorms that occur and the secondary phenomena of lightning, not the primary one where it hits the transformer, but secondary, what that will do to the transformer if it doesn't have the proper shielding.
We're requiring only 2 kV of surge testing on that charger's primaries. But I know for a fact that charger manufacturers, and I can't name any names here, are testing it twice that. You could put that charger inside a substation fence, it would meet these standards.
So we have another question from your friend Jerry Meyerhoff. He says, have the standards been benchmarked against legacy power systems, communication systems, such as smart meters to assess the risk to install systems?
Benchmarked, have they been benchmarked? No, there was no testing, Jer, if that answers your question. What we did is we followed Europe's lead, and we followed the American manufacturers who were selling into Europe's lead, like that Cisco and SEL ads that I showed you earlier. Said they were doing these documents, said they were hitting these levels in European Union. There's no reason that American products should be worse. And so we were ordered by the NIST SGIP to integrate or harmonize what was required in the IEC with what the IEEE pair of documents would require. So no, there was no benchmarking or external testing, but if you can get me some funding, I'll sure be happy to try.
Wonderful. So what I will do now is talk a little bit about next week. On the 12th of November, we'll have William Miller, who's very active in IEEE, talk about the XMPP standard, which is the Internet of Things, or one flavor of the Internet of Things work that's going on, and I understand there's been a lot of activity in Scandinavia and globally. So just a real quick thing on Internet of Things. Essentially, all your various touch points in life, imagine if they had intelligence and they were all connected over some type of a TCP/IP-based network, you could separate the actual phenomena of that device from the underlying network. That's the real beauty of the Internet of Things, is that every object can identify itself in this community. I'm a toaster, I'm a refrigerator, I am a radio. And there are certain features that are associated with that device. And there's a standard nomenclature for representing those attributes and standard messaging by which those attributes can be manipulated, controlled, or read from. That's the beauty of the Internet of Things, that you're taking enterprise networking to a whole different level where even appliances can be part of that community. So William Miller will talk about the XMPP standard and the progress that they've made in the past year. He also presented last year on the Smart Grid Educational Series. You've heard Cisco and Intel and other companies talking about it a lot in the media. I think it's really important to understand what's real and what's virtual. And right now there's a lot more virtual than there's real, but the commercials will show you otherwise. So William will come and tell us some real information, some tangible information.
I have some small bit of bad news.
Okay.
About the Internet of Things. If the Internet of Things is on the customer's side of the meter, and much of it will be, inside your house, for instance, that Nest thermostat, for instance, famous Internet of Things device, early adopters are buying them now. I know for a fact that they're doing EMC testing that's not legally required because they want their Nest thermostat to be worth its price, which is not cheap, and to be reliable, which makes it worth its price. There is no mandatory testing in the United States for immunity or resistance to outside interference on the customer's side of your meter. Outside your meter, up on the wires, and in the transmission and distribution substations we've been talking about today. But in this room, none of this applies. Emissions only, or protection of radio spectrum only applies. But manufacturers who want to succeed in the Internet of Things, in consumer environments or light industrial like this, will need to do EMC immunity testing or their products will simply be unreliable and you won't want to buy them.
And I will give you a tangible example of this for a house in the area here, Pleasanton, California, where there was a radio put, 17 dB radio put on the meter, and the place where the swimming pool was supposed to be, they just have a garden there, it was not getting the signal. It was like minus 70 dB by that point. And the reason why was that the fireplace had a metal lining in it that created a shield that blocked the access to the swimming pool from the meter. So a lot of people said, oh, well, it's a mesh. We can find another way. Unfortunately, there was no other node in between that would take it there. So you were basically out of commission. So this is the kind of EMI type of stuff that needs to be analyzed. You have to literally do a 2D mapping of the RSSI, the relative signal strength indicator, over that whole area of the house to know where those dark spots are, so that you can put the appropriate repeaters and things.
If you're going to sell those products in the European Union, you have a stronger regulatory structure there called regulatory compliance. I want to sell that thermostat over in Germany. Well, it has to not only meet emissions that protect the radio spectrum, conducted through the wires and radiated through space, but it also has to meet a modest set of immunities similar to the ones I've shown you, but not as extensive. Regulatory compliance. You meet your emissions and immunity requirements, or you're not allowed to sell. Here in the U.S., you only meet the emissions half. The immunity, which implies reliability, is not addressed. Those magical market forces are supposed to get you to take it back to the manufacturer, send it back to Home Depot where you bought it, and get your money back. And when they get enough of these back, manufacturers are supposed to magically figure out, this is crap that we're building. We should test it better. So I want to have a warning. If you would like to buy more reliable products on the consumer side of the meter, look for the CE mark, indicating it's available in Europe, which means it's had these immunity tests already done.
I think as a final note here, before we thank our host, I would like to suggest that if you are in the testing business, that you don't just test things a la carte. We have this culture of testing things, where we have a harness and we have the device, and we just test it a la carte.
Functional.
And we come up with X, Y, Z functions and say, okay, fine, it's good. Real environments are systems of systems, and there is interference amongst themselves. So until you don't create a simulation of that. Now, you can do this in software. with high-speed computing, you can simulate these things. But the best test is the physical test, where you put it in a lab just the way it will be in a substation or in a customer prem. Look at the interferences, document them, understand the operating regimes in which it will work, and provide that guideline to the customer so that they know under which scenario it's going to operate. That will distinguish the successful test lab from the not so successful going forward. The world is becoming increasingly more complicated, and the test labs have to demonstrate that same complexity in their testing. So the reason why I brought that up is because our host is a test lab. And so we'd like to thank Cetacom and thank Man and Gary and the whole team here who supported us today. And I want to thank, of course, Jerry for the great work he has done. Jerry does all the thankless jobs in IEEE. I mean, and this is why, if you look at his credentials, he's got a whole paragraph. It's about the equivalent of the ingredients on a piece of toast. If you look, you know, the sodium benzoate and all, he's got a whole paragraph of credentials underneath his name. So I match it with bread ingredients. And so that happens when you spend 3 decades or more working tirelessly as the secretary of this and the understudy for this. And John also, whose picture is here, has contributed a lot in our industry.
I couldn't say enough good things about the work of my friend John Tank.
Yeah.
John was not paid for his work. We slaved for the last 2.5 years trying to develop this document. And without John's unpaid slavery, formerly with General Electric head of sales, so he knows the utility markets well. Utilities trust him. The Power and Energy Society inherently trusts him. They don't know me very well, but they like him. And so John's my buddy, and he allows us to get things done in the Power and Energy Society without inducing fear.
The sad tragedy in technology is that the abolition of slavery of 1865 doesn't apply to technology. And so with all the civil rights movements we've had, when it comes to labs and when it comes to standards development, it just doesn't apply. And so I want to recognize those who continue in that state of enslavement, of their good work.
I see a question about the NIST thermostat in Florida died after a lightning strike.
Yeah.
NIST is a customer of ours and has bought the lightning strike test equipment to make sure that doesn't happen anymore.
Okay, very good. And please don't try this with the nests that the birds keep in the trees. That's a whole different kind of product. Okay, so with that, I'd like to thank our host, our speaker, and all of you, the audience here in Milpitas, as well as those online. As I mentioned, our next webinar is going to be on November the 12th at 12:30 Pacific with William Miller, talking about the Internet of Things and the XMPP standard. So at this time, I'm going to end the recording, and I'm going to wish all of you a wonderful rest of the week and a nice weekend coming up.